So here we are looking at the 2019 AP Chemistry FRQ question 6. It states that nitrogen dioxide, NO2 gas, is produced as a byproduct of the combustion of fossil fuels in internal combustion engines. At elevated temperatures, NO2 gas decomposes according to the equation below. 2NO2 gas goes to 2NO gas plus O2 gas. The concentration of the sample of NO2 gas is monitored as it decomposes and is recorded on the graph directly below. So this one right here. The next two graphs are derived from that data. So what they did is they, instead of graphing time versus concentration, they did time versus 1 over concentration and time versus the natural log of concentration. Explain how the graphs indicate that a reaction is second order. Really what's asking is, which graph gives you a straight line? And the only graph that really does give us a straight line, let me switch to the line tool really quick, there we go, is this one. Okay, straight line through all the points. The others are a kind of curve or a slightly less aggressive curve. So which one gives you a straight line tells you what order reaction you have. If this graph is a straight line, then it's a zero order reaction. Okay? So if time versus concentration is a straight line, that's a zero order reaction. If this graph down here, if this graph is a straight line, then it's a first order reaction. And then the last graph right here, if this graph is a straight line, then it's a second order reaction. Okay? So, notice how the AP people tried to make a mess for you. They didn't do 0 first, second. They did 0, 2, 1 to trip you up. So what you need to pay attention to is it's time versus what? Time versus concentration, zero order. Time versus 1 over concentration, second order. Time versus the natural log of concentration, first order. So the explanation here is explain how the graphs indicate the reaction is second order. All the graphs, the only graph that produces a straight line is time versus 1 over the concentration, which tells you it is a second order reaction. Done. End of story. Now for B and C, we have to get a little more nitty gritty. First, the rate law for this reaction, the reaction being right there. The rate law, how you write the rate law, it has some very important key factors. It will always be rate equals K, and it'll be all of your reactants. In this case, it would be NO2, and that's it. Now, this doesn't necessarily have to have the same prefix, or the power here doesn't actually necessarily have to match the prefix, but it can. Please keep in mind that rate laws are always experimentally determined. They are not derived from equations. However, in this particular case, we want to know the order, or we already know the order. We know that it's second order, and looking at the exponents on all, or the powers on all reactants, there's an implied 1 here currently, which means that this is currently a first order reaction. In order to make this a second order reaction, we need to make this a 2. And there we go. We have a second order rate law for this reaction because the only reactant is NO2. This rate law matches with the experimental data and accurately conveys and is only expressed in terms of reactants. Then C talks about 2 possible mechanisms for this rate law. The first is here with step 1 like this, which is slow, step 2, which is this, which is fast. C2 has step 1, step 2, with the second step being the slow step. Now, in order for a mechanism to be valid for a reaction, three things must be true. The first is that it needs to match the rate law. The second is that it must add up to the overall reaction. The third is that each step be an elementary step, which means that only either there are two molecules colliding or one molecule breaking down. Everything is either uni or bimolecular. So here we have two molecules combining. Here we have one molecule splitting up. Here we have two molecules colliding, then one molecule splitting up. So for elementary step reactions, they all make sense. Now let's check to make sure they both of these add up to the overall reaction. So the way we do this is we just put a little plus sign here, and we go, okay, everything that's a reactant adds together. So NO2 plus NO2 plus NO3 goes to NO plus NO plus NO3 plus O2. Then combine like terms and cancel out anything that shows up on both sides. So for instance, NO3 shows up here, NO3 shows up there, so it cancels out. That would be your intermediary, something that only occurs during the reaction. It isn't actually present or stay present for the complete reaction. Then when we combine like terms, there's two NO2s here, so it'd be 2 NO2 goes to 2NO plus O2. That matches that. And all the states of matter tags would need to be filled in. Sorry, I didn't write that down. So C1 has passed the first two criteria. Let's see if C2 does. Again, add everything up. NO2, NO2. So you have NO2 plus NO2 plus N2O4, single arrow. Why do we use a single arrow? Because we take the most determining reaction. This will go back and forth, but this will only go one way. Once it goes through this step, it's not going to go back through this step. So we use this single arrow to indicate this reaction is ultimately going to go a single direction. N2O4 plus 2NO plus O2. And again, our intermediaries cancel out. N2O4 is on both sides. So it's 2NO2, 2NO plus O2. So both these have met the first two criteria. They are all elementary step reactions. They add up to the overall reaction. Now we need to check the rate law. So let's go ahead, erase these. Erase the additions. We already checked they add up. Now we need to check the rate law. The way we write the rate law for any elementary step reaction, or really any reaction mechanism, is we find the rate determining step, which is always the slowest step. So for C1, it's step 1. For C2, it's step 2. And then because a reaction mechanism is a series of elementary steps, when you have an elementary step, and only when you have an elementary step, the prefix is the same, or the coefficient is the same as the exponent on your rate law. So for this one, let's write the rate law for the slow step. It's always going to be, once again, rate equals a constant times, write your reactants, NO2. And because there are two of them, we could do a squared. And hey, look, our rate law matches the calculated and found rate law, so therefore this reaction mechanism is valid. When you write that out, you would be something along the lines of, yes, because the first step is the rate determining step, and it is an elementary step reaction, the rate law would be rate equals KNO2 squared, which matches the determined rate law. Additionally, the reaction mechanism is viable since all the steps are either bi or unimolecular, meaning that there's one or two molecules colliding or interacting, and the mechanism adds up to the overall reaction. Fair, valid. C2, this rate determining step is this second one. So we would have rate equals K N2O4. But the problem here is that this is supposed to be the reaction or the rate law for this entire reaction, not just the intermediary. Because this is an intermediary, we can't use it. Whenever you write a rate law, it must be written only in terms of reactants. So in this case, we need to work backwards. We need to get this N2O4 in terms of something else. There are two ways to go about this. They ultimately give you the same goal, but let's talk about them over here. Option 1. Because this is an equilibrium reaction and it reaches this equilibrium very fast, what we can say is that the rate going forward equals the rate in reverse. Or in this, what that ultimately means then is that we could say it would be K NO2 squared, because there's 1, 2 of them, equals, let's change this from K to I just so they're easier to tell apart, equals J N2O4, which means that if I do a little bit of math here, I could say I over J NO2 squared equals N2O4. And then I can plug this in over here. That's good, fine, and dandy, but perhaps you didn't quite follow that. So we have option 2. Option 2 says, well, this is an equilibrium reaction, which means that there's going to be a K EQ, which in this case would be N2O4 over NO2 squared. Rearrange this to solve for the N2O4. You get K EQ, which is NO2 squared equals N2O4. Either way, pick whatever one you want, this term here or this term here, then plugs in for that N2O4, which would give us rate equals K, I'm going to put a little star next to it, NO2 squared. And therefore it matches the rate law. There is a little trick there, however. Notice how I have K star. This is because if in the first case with the red, I'd have K EQ times K, and with the orange, I'd have K times I over J. In either case, you have a bunch of numbers multiplied together. These numbers are all constants. They're not changing. So when you multiply a bunch of constants together, you just get another constant. So if I multiply K times KEQ, I get a new constant. If I multiply K times I times J, I get another constant, which is what I symbolized over here with K star. This rate law is consistent. Now, in both cases, you'd have to discuss how you got your rate law and why it's consistent. So something like for C1 would be, in this reaction mechanism, the rate determining step is the first step, which means that the rate law for that element first step would be rate equals KNO2, because it's an elementary step reaction. We know that the number or the coefficient is the same as the number of molecules. We know it's the rate determining step because it's the slow step. For C2, that would be something like, in this reaction, the rate determining step is the slow step. However, because that would give us rate law of rate equals K times N2, concentration of N2O4, which is an intermediary, we cannot use that reaction. We must then translate it. Since this first step is a fast equilibrium reaction, we can go that we know that there will be a KEQ expression with the products over the reactants. If we rearrange that and solve for the N2O4, we will get this expression, which we can plug in, and that would then simplify down to the rate law that matches the one that was experimentally found. Go ahead, feel free to ask questions about that, but that's a general explanation for number 6.